get started. So, hey everybody. Some of you might have been in one of these already. Some of you may not have been. But in any case, hello. My name is Elizabeth, president of the Rose Tech Radio Club, which is the amateur radio club on campus. If you're not familiar with what that is, basically it means we play with radios, we play with antennas, we play with signals, electricity, communications, all that stuff. It's a lot of fun. And this year, something that we want to kind of bring into campus is more of an exposure on, what kind of these options are in industry. There's kind of a lack of folks going into industry kind of with this background, with this interest. So we kind of want to expose all of you some options, things that you might want to pursue or look into. You look into an internship and, just kind of expand your horizons a little bit because it's really fun stuff. So yeah, today we've got Tony Milluzzi from Garmin, and I'll let him introduce himself, but he's an alum of the club and alum of the school, and he's got some real neat stuff to share with us today. So yeah, I'm excited. Take it away.
Awesome. Well, thank you for having me. I'm in here. There we go. I am currently an EMC engineer at Garmin. Been at Garmin for a little bit over 5 years. Went to Rose, graduated from Rose in 2016 in electrical engineering. Went on to do my master's at Ohio University and did research specifically on avionics there. So the whole aerospace avionics thing's kind of been in my blood for a while. Actually did research there for the FAA with some bird strike mitigation stuff, avian radars, ADS-B, which is airplane tracking data, if you're familiar. Did some cool stuff there. As Elizabeth mentioned, I was part of the ham radio club when I was at Rose, was the president a few years, was really active in that then, still am. Also, I'll give a plug here to the collegiate amateur radio program that I volunteer for with my brother. So if you're interested in radio or this spurs some interest in RF type stuff, there's some great outlets. The Rose Ham Radio Club is awesome. You guys have great equipment and facilities there, but there's even a wider world of it beyond just Rose. Also, I'm an instrument-rated commercial pilot. I mentioned that here because a lot of that does come into play on what I do. My job is pretty cool in that I get to mix my love for radio, my mix for aviation, and Garmin's a big supporter of people having that piloting experience to the extent that they help pay for some of it. So little pitch for Garmin, but if you're interested in working for Garmin or doing more aviation stuff, feel free to reach out. All of my contact stuff at the end, and come learn to fly while you work here and have Garmin pay for it. So that's pretty cool. Before I was EMC engineer here at Garmin, I was an aviation systems engineer. So a different team, kind of spanning a few different areas, doing some traditional systems engineering and also some of the market research type stuff and project management, et cetera. So I've been lucky to see a lot of Garmin aviation, and that's helped a lot in the EMC roles I'll get into. Previously, I spent a year as a GPS systems engineer at Honeywell also. And that was really cool experience. That was doing GPS receivers that go on airliners. So that's its own interesting world there. So I have a bit of a background on that. So I thought I'd give a little background on what Garmin does before we dive into this. I realize that a lot of people, probably Rose students especially, being more tech oriented, have heard of Garmin, but maybe not in the aviation space. Of course, we're really well known on the consumer side for all the smartwatches we do. And then we've got, outdoor stuff. So, GPS is for hiking. We've got golf stuff. We've got marine stuff. So stuff for your boat. We've got auto OEM now, which is GPS and infotainment systems for cars that are built by, actual car manufacturers. We'll put our systems in there. And then we also are in aviation. Within aviation, we kind of span the whole general aviation space. So that's everything from the Cessna 172 single engine piston in the top left to stuff up like that Citation XL in the top right, big private jets. We do everything from retrofit. In the bottom left corner, you'll see these little displays that look like the old steam gauges, quote unquote, in old airplanes that we've retrofitted, much more capable. some of those GPSs there in that middle stack. Those are some older GPSs actually, but they're still out there, all the way up to these really complicated integrated flight decks. And that's a lot of what I focus on in my job. But that's those displays you see there. That's actually our brand new, just announced G3000 Prime integrated flight deck. Those 5 displays are all touch screens. They control most of the system, and then we have a bunch of equipment that you don't see in the cockpit, stuff that's behind panels and in other places of the airplane for sensors, GPS, radios, transponders, data concentrators, radars, radar altimeter, et cetera. So we have a whole suite of equipment that we can integrate together to load your airplane to make it do all the coolest things ever. So it's easy to show these pictures and you see a little bit, but there's a whole lot of stuff behind the scenes that makes those screens do what we want them to, and we get to play with all of that in our day job. So a lot of fun. So what is electromagnetic compatibility? This might be a term that you've heard. I remember when I was at Rose, the doubles had to take EMAG, the actual class, and then the computer engineers took an electromagnetic compatibility class. Of course, this is the same space. It's the ability for equipment to work with other equipment without interfering really in a negative way. The key 3 topics there are emissions, which is the energy emitted or generated by the equipment, susceptibility, which is equipment's tendency to malfunction when it receives unwanted interference, and then coupling, which is the means of which that electromagnetic interference reaches the equipment. And we'll dive into coupling a little bit more as I describe the testing. But basically, this is ensuring that equipment can work together okay, not just not be destructively damaged by unwanted interference, but functionally work as you'd expect. And this spans all levels, right? You can look at, like, in a computer, you're going to do things with like the actual PCB traces on a circuit board to ensure that that signal integrity is good and the system works as intended, all the way up to what we're going to be talking about, which is in an airplane, all these systems need to work properly from an interference perspective and meet requirements to do so. So it's a pretty broad field. You'll also hear electromagnetic compatibility specifically in like compliance to radio standards. So like if you're building a cell phone, you've got a GPS in there, you've got a cell modem, you've got Bluetooth, Wi-Fi, and you have to make sure that all those will operate properly together. And there are regulations and compliance things you have to do to ensure that. That's a whole nother part of electromagnetic compatibility. As I'm going to talk about today, though, we're going to kind of focus in on the avionics world, which is really what we have to do to meet the requirements set out by this document called DO-160. And it's basically a giant list of different environmental tests that need to be done and what sort of levels you need to meet to pass the tests, depending on what the equipment needs to do. So we are constantly referencing this. This is an adopted industry standard that is pointed to from government regulation for aircraft to be certified to fly. So, if you go places other than Garmin, they might do things a little bit differently, but they're still using DO-160. It's well known. It's, and there's constantly revisions every few years. So it's a pretty important document. And I'll dive into a little bit more about it in a second. But at this point, I also wanted to kind of give a high-level view of this, that we are looking at, or we must consider both how the various singular pieces of equipment that go on an airplane function and that they are, electromagnetically compatible within themselves, and then also how the whole system acts together. My team really focuses on the system aspects, but that appliance level or the boxes individually do have their own requirements, undergo their own testing. That is handled really by our design team when they develop the product. But we need to make sure it works. And, when you take a step back from it, the conditions that really matter for an airplane is that you've got an airplane flying around in the environment, going past very high power radio transmitters, radio stations, the shortwave, maybe military radars that are out and about, that are always blasting energy. And we need to make sure the airplane doesn't crash because it goes somewhere close to those transmitters. And then the other aspect we really focus on in my team's testing is lightning strikes that are nearby, which are guaranteed to happen through the life of an aircraft. We need to make sure that that doesn't cause dangerous conditions on the aircraft as well. So that DO-160 document has all of these different sections of environmental conditions that must be tested. And this spans many teams at Garmin for actually testing them. So you've got everything from sections 4, 5, and 6, which are temperature, altitude, and humidity. Does the system or does the box function at specified high temperatures, low temperatures? Can it survive being stored at a really high temperature and then being used? What's the maximum short time temperature it can work at? There's a whole lot of testing there. It's a pretty wide range for airplanes. You have to consider things being sat out in Antarctica for days and then want to be turned on, and they have to function within certain time spans and et cetera. So a whole lot of stuff here. I won't go through them all, but some of the other really kind of complicated and big important ones are like vibration, especially with helicopters. That can be really hard to design for, and there's a lot of things you have to do to equipment to make it pass very high vibration levels. Sand and dust and waterproofness. Some of those seem easy, but when you're talking about these, what are basically computers in airplanes, you've got a lot of thermal management issues you have to deal with, and there's trade-offs there of managing that energy, but can't always just stick a fan on it. So for my team, though, like I said, we're focusing on sections 20 and 22, really, which are radio frequency susceptibility, both radiated and conducted, and I'll go into that, and then lightning-induced transient susceptibility. Now, you'll notice section 23 is direct lightning, so that's like lightning hitting the plane. Since our equipment is inside the plane, we don't really need to deal with the equipment getting hit by lightning, but when the airplane gets hit by lightning, how does that affect the systems inside it? That's kind of where we take off on our system level testing. So why does this matter? I mean, I talked about, that you could fly past a high power transmitter and that could be an issue. For one, we have to do this. There are regulations requiring this before airplanes can fly, industry-driven requirements, but they're pointed to by federal regulations. So we don't have a choice. The testing we do for this is costly, it's complicated, it takes a lot of time, but it's required. But more importantly, it isn't just an abstract thing. There have been many events over time where electromagnetic interference has caused some pretty bad situations. Really, in the 1970s, a lot more of aircraft designs were being shoveled towards electronic systems being flight critical. And that kind of kicked off the industry standardization of this testing. But there have been, events like you see here. I've got two in the 1990s. There were events that were past that period, and we're still having EMC-driven situations. So in the top right there was an Airship Industries airship that passed by a Voice of America shortwave antenna, high-power shortwave transmitter. Basically caused a failure in one of the systems powering the engines. They had to make an emergency landing. That was a big deal. And then bottom left there, Robinson R-44 helicopter, which they're still made today. It flew near a high-frequency radio antenna in Portugal, and then they started experiencing interference with their radios, navigation, and then they ended up losing the engine and had to go to forced auto rotation. So these things do happen. They can be bad. We'll get into kind of the specific failures that we're really concerned about and how we test for that. But the fact of the matter is there are more and more airplanes in the sky that are dependent on electronics to fly safely, and we need to make sure they can do that. Let's see. So I said there were two sections in DO-160 that my team really focuses on. The first is radio frequency susceptibility. We call it high intensity radiated fields, or HIRF. So you'll hear me refer to this as HIRF for the rest of the presentation. That has two components: conducted susceptibility and radiated. So conducted susceptibility is the equipment's capability to withstand interference that's coupled through the power lines or other signal lines that go into the equipment. So you think of all the wires in the airplane that connect all these boxes together. Energy can be coupled onto those wires, and then that goes into the box and can cause things to happen. Radiated susceptibility is the equipment's capability to withstand interference that is radiated through the air. So think of a box being in a direct field of a giant, a big antenna, blasting it with energy, and that energy actually gets into the box through like holes in the box, maybe like I said, the cooling fan opening. Maybe there's not a good shielding or sealing around the connectors, and at a high enough frequency that can go right through these tiny little holes. So that's kind of the game there. On the right, you see the frequency ranges versus the type of threat we're really worried about. So what you'll notice here is under 100 megahertz really is where the conducted susceptibility effects are the bigger driver. And that's because the wires tend to be at a length similar to a wavelength, so that energy is coupled well onto the wires. They act as a big antenna. That's why it named this every wire is an antenna, and that energy can flow through. As you get higher in frequency, in the hundreds of megahertz into gigahertz, now those wires don't look as good of an antenna. Energy will still couple onto it, but it's not as good of an antenna because now the wire is many wavelengths longer than the wavelength of interest. So that energy tends to go through apertures in the aircraft, through windows, other openings, and then make its way into equipment in the same way, through holes in the box for cooling or connectors, or where things are folded together or whatever. Any opening is really where that kind of effect is. So what that means is that for our testing, we actually do two things. We'll do one test where we're coupling energy onto the cable, and then another test where we're blasting the entire system with high power fields. And I'll have some pictures and talk through that a little bit more down a few slides. Section 22, the other one is the lightning-induced transient susceptibility. This we typically call indirect effects of lightning, or IEL. Again, two aspects of it. The first is pin injection testing. So this is just putting a high voltage signal basically into the pins that it could see from a nearby lightning event, and see if the equipment is physically damaged from all that energy going through it. This is something that our design engineering team does. You can design, inputs and outputs of boxes to withstand this. So that's part of the testing. But then the system level testing is this cable bundle testing. So similar to the conducted susceptibility thing I just talked about, where we try to blast energy onto a cable, we couple it, and it goes into the box. We do something similar with particular waveforms that have been developed to mimic what lightning could look like. This is our primary focus is functional upsets. So when this happens, we see how the system responds to it. Like data might go away or something might misbehave, versus damage to the actual system. But damage can occur from this coupled energy also. It's quite a bit of energy when we do the testing. You're hearing bangs from the energy going into the injection core. And if we've got like a design we're testing that might not be in an enclosure yet, we actually have to put protective casing around it, because you could have things like capacitors blow up from this. So you're pumping a lot of energy in. It could be pretty dramatic, but it's intended to mimic what energy could be coupled onto the wires from a nearby lightning strike for the system. So in terms of our HERF and IEL test process, I kind of wanted to step through the different areas with some pictures. We recently here at Garmin remodeled our old factory warehouse into a brand new aviation building, basically. We're in Kansas City here. That's headquarters of Garmin, but our main aviation facilities are also here. And part of that is this giant HERF and IEL lab. You're kind of seeing a third of it in this picture. This shows our lightning area, but I'll get a closer up view of that in a second. And then also our bench integration area. So the first thing we do when we get ready to test is we get a fully representative system set up on a metal bench, one of those tables. That is the actual aircraft harness. So like the aircraft manufacturer will build us a harness the exact same way, the exact same lengths that they would put in an airplane. We take it, we put it on those tables, we lay out all the cables, we hook up all the equipment together. We add in some places for our systems to monitor it for testing. We have to do some simulation To make things work right, we have to put electrical loads in different places to make sure things are representative. If we don't have the actual equipment there, the integration process is big and complicated and can take a lot of time. We face a lot of challenges of we're trying to make a system think it's an airplane on a table, and still be representative electrically of the original airplane. So like we can do simulations and loads, but we can't do anything that could also impact the test. So we'll often have to do some custom software that's tweaked in places to make this work. But integration is several months of effort, depending on how complicated the aircraft system is. And it can be pretty frustrating at times to make this part work. And we have to do that before we can start the test. And then here is kind of the main other third of the lab. And for HERF testing, we use anechoic and reverb chambers. On the left side there's 3 anechoic chambers. There's one way in the back corner you can't really see. That we'll use. That some of this is also used for our design teams for doing the box level tests, and that's actually primarily what the anechoics are used for. We've got 2 reverb chambers in the picture on the right side. Those white doors are the entrances to the reverb chambers. And we have a smaller reverb chamber that's out of frame. The size is important in that when you think about the kind of testing we do, and I'll go into a little bit more, you're trying to generate an electric field that reaches a certain value to test the entire system. The bigger the room you're trying to do that in, the more energy you have to pump into the room. And there are, physical limits to how strong of a field we can generate because of the room is a certain size. So if we have to test something at a very high level, we'll put it in the smaller chamber because we can do that with the amplifiers we have. And speaking of the amplifiers, those white racks there on the right side, those are all of our different amplifiers for different frequency ranges, different power ratings for our testing. We'll wheel those around to the test control area on the side of the chambers, plug them up, and then run the tests for those ranges. These tests take typically several months for the whole suite of tests, so it's a pretty complex process. So going into those chambers for HERF testing, I'll point on the left side, you see an anechoic chamber and a system. This is actually one of our older anechoic chambers from our old building. Our new ones have this white foam over the cones to protect it, and actually makes it look a little more futuristic, but it's the same principle. This was actually pulled from a YouTube video. If you're familiar with Flight Chops, who's a general aviation YouTuber, he came to Garmin a couple of years ago and got a tour, and I pulled a couple screenshots there on the left. And on the right, it's a picture we took here of the new lab. But on the left side, you'll see on the top, those are 2 of our G5 electronic flight displays. They show your primary flight information, your airspeed, your altitude, your heading, your attitude. And in this case, they're on that table connected to 4 servos and a mode controller for an autopilot. So these 2 little displays are driving an autopilot. This is a retrofit system. This is much simpler than what my team usually works on. But here we'll blast it with radio signals basically to make sure it doesn't get upset. In this case, you're doing an autopilot. You want to make sure that the servos don't start moving on their own. You want to make sure they go the right direction. You want to make sure that the attitude doesn't just flip over, or you just don't lose values, or really worse, something's misleading where there's no indication on the system that something is wrong, and it's a valid situation, but not for what the actual conditions are. So we'll do that testing in these chambers. The anechoic chamber in this case, we would put antennas and aim it at the equipment and blast it with the signals to do it. We don't actually need the anechoic aspect for that, but we do need a electrically shielded and sealed room, a Faraday cage to protect us, because those fields can be pretty powerful. You'll also see against the wall those 2 boxes with copper tape. Those are cameras that we have. Since we have, in this case, servos and displays, we actually watch a video feed and record it to make sure we catch anything that could go wrong. And they're in those boxes because if they're not, then the cameras will get upset by the radio signal. So It's a pretty cool setup, but seems a little space age. On the right side is a reverb chamber. This is one of our new chambers. And what we're doing in here is really the same thing. We'll have a setup on this table and we'll blast it with high power radio signals. But the reverb chamber lets us tweak the room to ensure we get the adequate electric field level throughout it. So the best way to think about it is like your microwave that will have a spinning dish in it, and that's so that the food heats evenly and is always exposed to the electric field. The reverb chamber works the same way, except we're effectively rotating the room instead. So this giant paddle in the back will rotate, and we've got antennas in here that are blasting it with the signals, and then that paddle will rotate, and we do a whole calibration thing beforehand. But basically, throughout that whole rotation of that paddle, that ensures that the entire system that is on the table, it all reaches the proper level that needs to be tested to. So that speeds things up versus the anechoic chamber, where we have to go in and move stuff around a lot more. And like I said, we have a smaller reverb chamber also for even higher levels, but it's the same principle. It has a movable paddle, which is a giant metal paddle that physically rotates to rotate the room and make sure we hit the proper levels. And then getting into IEL testing, lightning testing. Don't have as cool of pictures here really. But on the left, that is one of it's the same table that would go in the anechoic or the reverb chamber for the HERF testing. It's the fully representative system. You can actually kind of see in the back where there's those little fans on top of the metal case. Those are displays. You're just seeing the back end of them. We've got the cameras up there too. And then we take this lightning generator, which is in the right picture with the monitor on it. We move it around and we put this giant metal induction core around each of the cable bundles right near the connector, and we blast it with those different waveforms, very high energy, and make sure that we don't see any upsets. So this can take a decent amount of time. And actually, I guess I didn't mention on the HERF side, the reverb aspect, all that's all radiated emissions. For conducted emissions, we actually do something similar to IEL, where we put a giant core on the cable bundles and we do a sweep of the frequencies. But in IEL, we're doing a specific waveform at a high power versus kind of a generalized signal over the span for conducted susceptibility. So they're different tests, and there are things that only happen in radiated. There are things that only happen in conducted. There are things that only happen in IEL testing that we see. You'll see a lot more instantaneous failures in IEL that quickly come back because they just have to react to a bunch of energy, then they go away, versus a lot of the other types of failures can be slower going. So it's cool. It is dangerous if you're not careful. We have procedures for it. We actually have to stand back about a meter from where the injection core is for IEL. Otherwise, you reach a higher level of magnetic field than OSHA allows. So we have signs for people with pacemakers not to be in the area when we're doing this testing. There's some serious effects you have to be careful of. But yeah, it's pretty cool stuff. And like I said, it's every connector to every piece of equipment we need to test that meets a certain level of criticality, which I'll get to in a second. But it can be time consuming for that reason. So what are we looking for during all that testing? We're hitting it with all these waveforms and high power radio waves. We're looking for indications of susceptibilities that we call upsets. And those are usually shown where data that's maybe on the screens just disappears. It goes, we get dashes or a red X indicating it lost it. Those could be temporary or permanent. Maybe they go away and you have to power cycle the system to get them back. Misleading data. So suddenly it shows that your airspeed has increased significantly, but the airspeed actually didn't, but the data is shown to. That's considered misleading data. On displays, we'll see a lot of flickers or flashes. One of the things to think about on these displays is that they're basically a giant window into the metal box. You can shield them in some ways, but they can let a lot of energy through inherently. So displays are always tricky, and you'll see displays flicker and do all weird things during testing at high levels. And then you can also get equipment just locking up or getting into a particular state and staying there, kind of like the permanent loss of data scenario, but you might need to reboot it. It triggers something that keeps it in a particular state. But just because there is an upset doesn't mean the system failed. We actually consider the function that had an upset and the criticality associated with it. So on the right, there is a table for all the different failures that an airplane could have. They do these huge tables of failures, and they can be catastrophic, hazardous, major, minor, no safety effect. Basically, we categorize the failure based on how bad it is to the aircraft and the people on it. So as you can see, a catastrophic failure is something that would prevent the safe flight and landing of the rotorcraft or airplane. Basically, a catastrophic failure means there's a good chance someone's going to die because the airplane's going to crash. So those are very serious. And those are things we definitely want to make sure we test so that they don't happen. Hazardous is kind of a step below that. So you're significantly reducing the capability of the airplane or the ability of the flight crew to respond. Very dangerous. Maybe someone gets injured, but not necessarily, the plane crashes. Then we go down to major, where now you're reducing the capability or the ability of the flight crew, but not significantly. So they categorize these, and what it means for us is basically major, hazardous, and catastrophic failure conditions are ones that we have to be concerned about for our system level HERF and IEL testing. Just because if they happen, the outcome could be so bad that we need to make sure they won't happen in these conditions. Like I said, the events where airplanes have flown too close to transmitters has happened. It doesn't happen all the time, but we need to know that when it does happen, that the plane is not going to go down. So we categorize it and react effective or alongside that. One of the other interesting things to consider is when you look at those catastrophic failure conditions and the levels we have to meet, we actually kind of split it beyond that into a control versus display aspect. So you've got, for example, if you lost all your flight instruments, that would be at a high, that'd be a catastrophic event. We test it to a level for losing the display aspects because you couldn't see what you were doing on the airplane, but it wouldn't inherently crash. But if a system that's controlling the autopilot gets into a condition that just drives it towards the ground, that's even a higher level because now you've taken the pilot out of the loop to do anything about it. They could notice it and stop it potentially, but when the airplane is doing things more autonomously, we need to hold that to an even higher level than if just the pilot is flying it manually and has some sort of event. We still take credit for the fact that having a pilot in the loop mitigates some of the danger there. So what can we do about it? Well, the short answer is if we find something when we're doing our system level testing in those chambers with the whole system connected and functional, it's basically too late. It's really costly to fix at that point. We'll have problems that we notice, we'll have upsets, but typically they're not at a level that derails the whole test, and that means something big has to change. At this point, we have a lot of experience on what can happen with certain systems, and we have good practices to avoid that. But it's very costly to mitigate that late in the game because we're actually one of the last tests that happen before the aircraft gets certified because we need a high level of maturity of the system just to do the test. So really, we prefer to be in the loop up front when both the boxes on the airplane are being designed individually and when the aircraft system architecture comes together where they start putting those boxes together and figuring out how they'll connect. Some of the things alongside that is, we don't need every single piece of equipment to meet the same levels. You might say, well, why don't we make everything catastrophic or meet the levels of catastrophic? That'd be super safe. It would be incredibly expensive and complicated, and it would take forever to do, and it's not necessary. You look at functions, maybe something like a transponder, which lets air traffic control and other airplanes see where you are. It's an important piece of equipment, but if that goes out, there's a lot of other links in the chain that can prevent something catastrophic from happening. So that doesn't necessarily meet the same level as your autopilot. So, we are careful in how we architect the system and what we need to require certain pieces to do. Also, we can take advantage of where things are installed in the aircraft. Like I said, the whole radiated emissions is through apertures and openings, maybe through windows in the airplane. So some equipment is going to be in a avionics bay. That is, there is no windows. It's down below where the people sit. It's shielded in a much better way inherently. So if we can move more equipment there versus being out in the cockpit, that could be advantageous. So we'll do those types of design pieces. We'll design our wiring harnesses with EMC requirements in mind. There's a lot that goes into making sure a wiring harness is reliable mechanically, electrically, and that is not susceptible, or is the least amount of susceptibility as possible for EMC. One thing I mentioned, or I put up on the top right there, is that's a table of Ethernet standards and their data rates, the number of pairs of wire in that is needed, and the frequency at which they operate at. And you'll see there, of course, the lower data rate Ethernet standards need fewer pairs of wire, and they operate at a lower frequency. And as those speeds increase, obviously, you need more wires, more or higher frequency. It might sound great to say, let's make everything work at a gigabit, make every Ethernet interface a gigabit. Ethernet's something we use a lot in our systems, but that's much more susceptible. And when you really get down to it, a lot of systems don't need a gigabit in an airplane. You're not watching movies on the avionics. You're doing other things that aren't that sort of data rate. So designing the system with that type of thinking in mind, not over specifying equipment to do more than it really needs to, because that opens the door for a lot of other issues down the line. And then also alongside the where you install the equipment, minimizing large openings in equipment. This is a huge trade-off with thermal management, especially. You can't stick fans on everything because you can have openings in the equipment because of that. So if you can make your boxes, machined boxes that sit together nicely with EMC shielding or like gaskets around the openings, that's a big deal. So those types of aspects, just getting on the same page on how we're going to architect the system and design it. And of course, a lot of these things, there are ideal design practices that we can put in place to make them pretty immune. Like, a lot of this isn't that we don't know how to make it immune. It's that it's just too expensive, or it's too complex to install, or too heavy to do so. As the airplanes get bigger, the more and more cable you get, the heavier it is, the more shields on those cables, the heavier they get. The number of pairs of wires comes into play there. But you also look at things like, these airplanes need to last decades. And if you're using something like a gasket that is meant to prevent EMI or interference coming through, as things open and close, those gaskets wear down. How do you guarantee they last for a long time? And if they don't, they need to be replaced. That's very expensive. So those are the types of things we face. And the other thing I'll point out is that hardware changes can be a challenge. Especially, over the past few years, the whole parts shortages things, we weren't immune to that. That supplier changes, or even we make a better design, that can affect EMC's testing. So whenever someone wants to make a change to the hardware of the box, we have to evaluate whether that invalidates our previous testing, whether we need to do more testing, or maybe we just need to do a formal analysis. These things stick around for a long time. So decisions made early on stick around for a long time, and we're always in the loop, even long after the aircraft is in the field and being made on the assembly line. And then one last thing I want to throw in here before I open for questions is software. And this has been a very hardware-oriented presentation, and my team is in the electrical engineering group, but software is actually really important in all this too. It can help us and it can hurt us. So you can make software, or you can have software help make the system more resilient and reliable in terms of EMC. You use digital filtering, you can have debalancing techniques, you put in good logic for different functions for how it will react. So for example, maybe you require the system to get 5 samples of some data before it considers it for measurement and usage throughout the system. And that could be a way of mitigating EMC where you're not necessarily, the chances of one sample being affected by interference could be much higher than 5. So that's a means to do that. So those types of things go into play. We do different software techniques to make our system more resilient to interference. It's good design practice, but you also have to be careful that you're not inadvertently masking problems. The EMC team, we can understand software when you talk us through it, but we're not software engineers. So we need to know how it works to some extent and make sure that our system testing is actually exercising the software in a valid way. That same type of needing multiple samples aspect, if we don't know that that's how the system's designed and we're not, keeping the system under test long enough with interference for multiple samples, that could be an issue. So software is a big help, can be a big help, but we need to understand it, and it can have big impacts on EMC testing. And then on the other end, the software has to be mature enough to do our testing. Like I said, our testing is kind of at the end of most projects because we need maturity across everything. But there is typically software changes that are made after our testing, and we have to analyze and validate all of those changes to make sure that it does not, affect the testing we did. And we really rely on software engineers to help us understand those changes. We actually have them do the initial. We have kind of a question form that asks some basic questions of things we might be concerned about. We ask them to go through that first to let us know, is this something we should even care about? Is it's an actual functional change to the system that EMC, it could affect EMC. And then we go in and review that and then work with the software engineers to get to better understand what happened. So again, on the hardware side, you've got parts obsolescence and part shortages and design improvements over the years. That means that things live on. Same thing with software. And software, because it's so quick and easy to change, there is always a drive to make those changes in software as soon as a bug is found, which is great. But we need to make sure that EMC is aware of it so that we can look at it too. So that's all I had for today. There's a lot more detail on this. I'm happy to talk about more, happy to answer some questions. And if you want to reach out, my email address is there. Feel free to do so, whether that be about EMC, Garmin, anything. Happy to help.
Okay, everybody, can we give Tony a quick hand? Sweet, okay. Yeah, before we transition out, does anyone have any questions? Okay, let's go here and then we'll go here.
So you said that the anechoic chamber has to be scaled up for higher power tests, but if the absorber cones aren't actually being used for like the anechoicness, like I thought the only power limit was because of like the power limit on those cones, like a given like energy density on those cones. Why do you have any idea why you need to scale the chamber size up for the higher power tests?
So we would actually scale the chamber size down for higher power. So we have a smaller, we typically do our radiated testing in our reverb chambers now. It's a lot simpler, but we have a smaller reverb chamber that can go to a much higher level because it's a smaller space that needs the field to reach a certain level. So that's the case there.
Oh, that makes a lot more sense. Thank you.
Yeah.
And then I was also wondering for the lightning testing, I think it was like IEC, not direct strike, but the induced, I guess maybe that was direct.
Yeah, indirect effects of lightning.
Yeah, the one with the induced magnetic field part, how do you fare against, like, because it can, like in the real application, could have come from anywhere in the system, but you have to, kind of stick your coil right up to like your main circuitry. And are you not concerned of any like permeability concerns, like, oh, like you're getting like a capacitor failure because they're like nickel plated terminations because you have this huge coil right next to it with like an insane magnetic field spike? Like, isn't that a bit different than the real application, but like the real instance of induced current where it's like somewhere else in the plane there was like a strike and that induced current into your coil, into your circuit, but in your test you're like blasting it with magnetic fields. It's like not.
Yeah, so the test can be either a voltage or current waveform depending on a few things. And we're testing every single connector on essentially on every single piece of equipment to that level. So we're seeing as if everything got hit at some point with that high level. The case is really like the airplane got hit and some things got inside and within the airplane could affect it. The actual waveforms and the whole procedure was developed based on some real world data collection. I can't remember, it was a NASA or something did, plus some modeling and some simplification to make things representative of the effects that the equipment sees from a nearby lightning event. But yeah, I mean, there's also some aspects like we do the multiple bursts, multiple strokes. We add some randomness into when the strikes happen in succession for some of that testing, and some of that's kind of a pseudo randomness. So is it exactly the same? Definitely not. But we see the same or similar representative effects.
Thank you.
Okay, cool. You want to ask?
Yeah, and I had 2 questions. I was wondering first, are you able to actually detect when there's an upset in the system, like from a software perspective or hardware perspective, and then like notify the pilot, hey, something went wrong?
So yes, we don't really put in alerts that are like you had a HERF event, but we have extensive monitoring. So we have, as a part of the aircraft systems, we've got extensive monitoring of systems for all sorts of behavior. When something gets weird, it can alert the pilots. So we do have that to some extent. We also, for our testing purposes, we add additional monitoring to the system. So we'll tap different different lines of the system and monitor them and get data feeds to see what they're actually doing. And we've got some automation that helps alert us to that fact. But we also record it all, post-process it, et cetera. So there is some testing on both ends. But some of the difficult cases are actually like the misleading stuff I talked about, where the data that's being presented to the pilot, it's a valid piece of data. Like it's not outside the bounds of what could happen, but it does not match the real world. And if the pilot has no way of knowing it does not match the real world, that's a problem. And that can be really hard for us to self-monitor within the system because it could be a valid case in some scenario, but we have no way of really monitoring that. So we have to make the system resistant enough to that.
Okay, that makes sense. And then my other question was, I was wondering if you saw more coupling than you actually saw in like the real plane whenever you do the model system, since all the wires are, I guess, closer together than they would be if they were laid out on the plane.
Yeah, so that's a good point. There are some there are definitely some there are some simplifications that have to be made. For example, you see, or yes, they have to be made, period. We try to do our best to do worst case testing inside what's reasonable. For example, you saw that pink foam. That's like insulation foam board. It's the same stuff you put in the walls. There's definitely some like industry standard stuff that's really expensive, but the purpose of that is that you have to be a minimum of 2 inches away from what would be a ground plane or the aircraft, skin essentially. And then you have bonding straps from each piece of equipment to that common ground. And those minimum lengths are set up to create a representative, and in some cases, worst case scenario for testing that. So yes, you could definitely say that like, okay, you've got all these cables laid out on this bench. If there's a ton of cables, they're overlapping, et cetera. How do you know that everything really gets to the same level when you're doing the radiator testing? That's true. But we do our best to do a worst case scenario by ensuring things are set up in a worst case way that is reasonable, and then also over testing. We might test at higher levels than we have to give ourselves some margin for some of those types of things that we can't easily quantify in our test reports.
Thank you.
Anyone have maybe one more question before we wrap up? No? Okay, yeah, good questions, gang. Thanks. Yeah, this is super cool. I mean, I've done like some electromagnetic compatibility stuff, but like at a small scale. So like seeing kind of what goes into it at like such a larger scale, that's really cool. Okay, Everyone, thanks for coming. It's Free Pack Up Radio Club kiddos. You wouldn't mind sticking around a couple of minutes, but yeah, thanks for coming and thank you, Tony.
Yep, thanks. Thanks, everyone.